Hello everyone and welcome to another video. So today we are on to week 7 of our AE511 class. So the roadmap of where we're headed this week is we are going to continue our discussion on closed loop control design via the root locus technique and jump right into that in week 7. Well, actually, to be honest, not exactly jump right into it. The first thing we're going to do during week 7 here is have a quick discussion on bandwidth of a dynamic system. So bandwidth is another performance metric. You know, we talked earlier about things like percent overshoot, rise time, settling time, things like that. The bandwidth of a dynamic system is another very common performance metric that will be important. And we're going to see that the bandwidth of a dynamic system is usually a function of the type of control system and your control design. So this is relevant now as we're designing closed loop control systems. We're going to want to make sure that we meet various performance criteria, including the bandwidth of a dynamic system. So that's what I want to talk about right here in this first discussion. But then what I'd like to get into is probably the most popular type of closed loop control system in the world. Full stop, period. Right? That's the idea of proportional integral derivative, or PID control. So I'd like to take a quick look at just what is PID control, how do we use it, how do we design a controller for this, and look at it from a very academic perspective. The reason I say academic perspective is because if we take a sneak peek into maybe week 8, later on we will talk a little bit about some practical implementation issues that you might encounter with a PID controller. But for now, during week 7, let's just leave it at a very high academic, sterile mathematical discussion. We'll talk about practical implementation next week, but for now, let's just talk about what is PID control. And then what we're going to see is that we can actually start thinking about designing a PID controller using some of these root locus techniques that we talked about earlier. So in order to do that, one of the first things that we're going to want to be able to do is talk about how do the different pole locations relate to different performance metrics like bandwidth or rise time or settling time or things like that, right? Remember in our earlier week, we talked about all these different performance metrics and how they're related to plant parameters. Well, we can see that they're actually going to be related to pole locations. That's really what it all boils down to at the end of the day is in order to get a specific set of performance, you're going to want to make sure that you put your closed loop poles in a certain location. So what this discussion is going to look at is what is that relationship between pole locations and performance criteria. Once we're able to do that, we're going to now marry that idea with root locus, right? Because this here is saying, hey, put your poles in a certain location, you will get certain performance. Root locus says, hey, if you vary a control parameter or a gain, you will move the closed loop poles to different locations as defined by the root locus. So really, if you combine that with the previous discussion, you can see that we can basically use root locus to directly try and meet performance requirements. So we're going to use the root locus technique to synthesize controllers that meet performance criteria like percent overshoot, rise time, bandwidth, etc., right? So that's what this first set of discussions is. It's basically a mathematical theoretical discussion of how to make that happen. What I want to finish out week 7 this week then is, like we've done in the past, let's first introduce the theory and then let's look at an actual computer tool. So MATLAB has a system called the Control System Designer, which is going to allow us to do a lot of this workflow that we talked about for all of these videos here. It's going to package this in one nice designer tool that's going to allow us to do all of this in one shot. So I'd like to look at that, see how we can use the MATLAB Control System Designer to basically design different types of controllers using the root locus technique. So that's what we're doing. That should be exciting because we're going to see later that's going to allow us to directly synthesize PID controllers. So we are going to talk about that again, priming the pump. We're going to jump into that during week 8. So for now, let's just get the tools in place, and then next week we'll actually apply that to our PID controller. Okay, so that's the game plan for week 7. Let's take a look at homework 7. And homework 7 is actually kind of fun because it's actually going to reference some of our old homework. So for problem number 1, I want everyone to remember and recall, remember back in homework 2, problem 4? In fact, let me pull that up. And maybe so I can put this over here on this side of the screen. You remember this system over here in homework 2, problem 4? We had this sort of mass spring damper effectively, but it was this rotating mechanism, and we did all this analysis. We built a Simulink model of it. We took a small angle approximation and made a linear model of it. Well, that's what this was, right? We said that you have a linear second order system if you're only looking at small angles. Now in problem 4 homework 2, we just looked at the open loop system basically and said, how does this system behave by itself, right? So in part A, you should be able to find the transfer function of theta to u, right? Basically input to output, right? What is that transfer function? You should be able to do that right off the bat. Now though, the fun thing now is we're in a position to be able to design a control system that will hopefully use this control input u to achieve a desired angular displacement theta, okay? So we're going to use this simple architecture that we've been talking about before, right? Now what we're going to do is let's try to use a PI controller, which has this type of control law. And again, if you watch the video on PID control, you'll see what this is. This will make a lot of sense. And you should then be able to actually say, okay, if this is the control law that my controller block C is implementing, you should be able to compute its transfer function right here, okay? And now, let's say the game now is, okay, I need to pick a KP and a KI value for this controller, right? That's what it means to tune a controller, is to pick these numbers so you get the overall performance to be something desirable, okay? So let's pretend that maybe you decide to just set the gain KI to 10. That's going to be fixed. And now what we want to do is we're going to use root locus techniques to find this gain KP. We're going to vary this gain KP from some minimum to some maximum number and see where do the roots of the system go, right? Let's go ahead and compute the root locus or sketch the root locus for this system as I vary K between these values. Now, the only thing I want to think about right now is you're going to have to explain here, actually, the techniques that we described back here in week 6 are actually probably not going to apply for this particular situation. And I'd like you to think about why. And maybe as a quick hint to this, maybe what I'll ask you to do is go back to our root locus discussion and think about what was the underlying assumption or the underlying architecture of what the controller looked like when we developed all of these tools and these techniques for sketching the root locus. You're going to see that in this particular case, a lot of those don't actually apply right here, okay? So that's some interesting food for thought, because you almost might think, wait a second, this is like about the simplest controls, well, not the simplest, but it's a pretty simple controller. And if all of this talk we had in week 6 isn't applicable here, why did we do that, right? Well, the reason we're doing that is because the exact techniques aren't going to work, but you should be able to adapt them pretty easily to fit this picture right here. And that's what being a control engineer is about, is adapting existing tools to your current framework or your current problem, okay? So that's what part C is about. Now what I'd like you to do in part D is basically go ahead and brute force compute the root locus as KP varies between these two values, okay? And again, I'm not going to talk too much about this because I want people to think about this a little bit. What do we mean by brute force? I mean just use a computer tool or MATLAB to basically go through and compute the root locus using numerical techniques, okay? And maybe I'll leave that for now. I don't want to give too much of this away. I think it's fun exercise for people to do this and think about this, and I'm happy to talk about this during office hours. Once you've got that, you could actually still use the Routh-Hurwitz stability criteria to determine which gains KP are neutrally stable, right? And again, if you need a refresher on what that was, remember we talked about what Routh-Hurwitz was last week, okay? And now, once you have that magical number which yields numerical neutral stability, I'd like you to simulate this system for 3 cases. Pick a KP which is actually unstable, use the KP from part E which is neutrally stable, and then pick a KP which yields a stable system. And just simulate it and just show me what the results are. Just play with this problem a little bit. I think it's a fun problem. It's good for looking at how we can use root locus techniques to design this very simple PI controller, and then we can simulate and see what happens. So that's what problem 1 is all about. Okay, so for problem 2, we're also going to be going back to the homework well, and let's go back to homework 5, problem 2. So again, let me pull that up just to refresh everyone's memory. Homework 5, Problem 2 was the one where we basically went through and you built yourself a planar model vehicle. So this was a nonlinear planar model vehicle, and if you recall, that is what we talked about back here in week 5, right? It was this discussion back here, and that homework was basically involving building a Simulink model of this and basically just simulating the open loop plant, making sure that you could generate trajectories that looked like this. But again, we just chose an input to the system to be something somewhat random, okay? So what I'd like to look at now in homework 7 is, okay, we are going to now manually create a PI controller that will control the velocity. So you want to make sure that you can use the U1 signal to basically accelerate the vehicle and control the velocity. And what I'm looking for here is we're just manually tuning this. So forget about root locus or any of these other techniques. Just this is effectively guess and check, right? This is play with PI values or the KP and the KI values until you get something that seems reasonable, right? So that's all I'm asking for right here is just use a PI controller and just play around with it and check a couple of the items. And maybe, if you'd like, go ahead and see what happens if you add a derivative component to this controller. So make it a full PID controller. First design the P and the I components, and then just add a small derivative and see what happens. Okay? All right. Then for part C is we're going to use a full PID controller to control the angle. So again, what you're probably going to use here is you're going to use the transfer function between U2 and the angle, and basically make sure that your system can track a specific heading. Okay, so again, both of these problems are basically an investigation of manual playing guess and check. You're going to run the simulation, change the numbers, run the simulation, change the numbers, run the simulation. So you're probably going to want to set up a script which makes it very easy to go ahead and evaluate performance. And again, don't overthink this and don't make this too complicated. All we want to do is just get numbers that are within a ballpark of reasonableness. So what we're trying to do is basically build this type of a control system where the plant is your planar vehicle, and you're actually going to have two controllers here. One controller is going to use U1, right, to go ahead and control the velocity, and the second controller is going to use U2 to control the heading angle. So at the end of the day, hopefully you have a simulation of this planar vehicle where you can specify a speed you want it to hold and then a heading that you want it to hold, and hopefully things will work out. Okay, so the last part is basically just demonstrate that things are working out, right? Just try to make the vehicle do a couple of maneuvers and see what happens. Okay, and again, we're going to play with this a little bit further later in the class and look at a little bit more formal techniques of doing this. Right now, I just want you to play with this and basically get something in the neighborhood of working, and then we're going to optimize this using formal techniques down the road. So, with that being said, I think this is probably a good spot to leave it. This is where we're headed this week. If you have any questions, again, shoot me an email. Otherwise, I'm going to look forward to talking with people at office hours. All right, thanks everyone. Bye.